So as I've been recording these videos, I've been very careful to follow good programming habits and, for example, free up any memory after I've allocated it, stay within my array boundaries, things like that. But what happens if you don't follow those good programming habits? What happens if you kind of break the rules? How much trouble can you get in? So in this video, I wanted to show a couple of examples of what not to do in C, just so you can see what happens when you're not following good programming behaviors. So let's do a first program here. We're going to read some long strings. You remember when we normally read in strings, we're trying to read in strings into an array or a string array that has enough room to store the string that we're trying to read, and we usually do a function like fgetS, which will let us limit how much data we're going to read, or we use getLine to read an arbitrarily long string. So let's do a sample program here, include standard IO, and we're going to do some string stuff. Let's do string.h. And there's our main function. Now let's see what happens if we read in a string data that is actually too long for the string we're trying to store it in. So char string, we're going to make this very short. Let's make it 3 characters long. And if you remember, that's going to give me strings like hi. That's 2 letters, and then at the end is a null value, and that's why it's 3 characters long. That string is 3 characters long. So it actually is holding on to 2 actual letters, and then hiding at the very end is the null value. So it's a null terminated string. So let's go ahead and print a prompt. So we'll do put s, what is your name? That might be a simple thing that you might do in a simple program to identify maybe the player. And then we're going to go ahead and read a string. Now again, normally I say let's use fgetS, because that lets you tell fgetS how many characters to read up to, so you don't overload your string. Or you might use getLine or something like that. What if we just use getS? Very dangerous function, because you're not telling it how much to read up to. You're just saying read that whole string. Pretend like this never exists in your C library, and you'll be much better off. Let's go ahead and print out what we've got. So we'll do printf, and we'll just put the string inside these brackets, %s. And then let's do the length. So the length of that string is, and then that's the length of the string. So we'll do string, and then the strlen at string. There's the end of my printf. And then let's print something else just to make sure that we got to the end. I could do another put s, but let's do something that actually uses some other variable values. We'll do printf. We'll print out like an xy pair, and that is going to be that. And I'll need to actually make those variables here. And that's x and y. And then I can return back the operating system. So before I'm done here, let's actually go ahead and create int x, and we'll give that a value of 1, and int y, and we'll give that a value of 2. Right? All I'm really doing here is I'm printing out a prompt, and I'm reading in a string using a very dangerous function called getS, because it's not going to care how long that string is, and I'm only giving it a string that's 3 characters long. It's going to then print out what I read in, and then how long that string was, and it's going to do some other nonsense thing just to see that we got there. That's all this printf xy thing is actually doing, just showing that we made it to that line. And let's go ahead and save and quit. And let's compile our program. So let's do it under the IA16 version of GCC first. So I16 GCC, turn on all warnings, and we'll save it as, we're going to compile this as well under OpenWatcom. Let's name this a little different thing so we actually know which one we're running. So we'll call this one glongster.exe, and we'll compile the longster.c file. And I don't have any warnings, so that was a good program, right? So let's go ahead and run the Watcom compiler and linker on longster.c. And I'm not seeing anything that's a problem in there, so that's all good. So I've got 2 executable files. Let's go ahead and run them. Let's run longster.exe. So what is your name? So again, it's very safe to put in short values like hi, right? That's That's exactly 3 characters, including the null. And so that's fine, right? No problems there. But what if I run that again and put in much more data than that string can hold? So I might put in hello world. That's a very long string. And what happens if I hit return? Well, I just kind of broken the system. My system is hung up. So that's what happens if you try to read in more data. You can actually break your system, because you notice we've not gotten that. We've not gotten a command prompt back. We've actually we're able to go beyond and actually print out that XY thing, but we haven't hit the line where it actually returns back the operating system. So let's go ahead and reboot my system here real quick. We'll try that one more time. Now I'm making sure that I'm loading this without drivers so that nobody says, oh, but your memory manager or something's getting in the way. So no, this is all running without any kind of memory managers and bugs. And so let's, that was the long stir that we just ran. Let's run G long stir. So again, I can put in a short value, and that's, but G long stir with something long like hello world, that's much longer than my string can take. What happens there? I get a very nice invalid opcode. So we still broke it. And oh, look at that. XY is not 1, 2. XY has picked up some other values from the system, probably because hello world has overwritten that with some bit pattern that XY was using in that memory address. So yeah, if you read in more data into a string or an array than you actually are allowed to, you can cause some pretty big problems. So never use getS. Always use fgetS or something. Let's do another example. So people often assume that variables will get initialized to 0, and that's not really guaranteed. So let's do another one here called vars. And so we'll do, again, include standard IO. There's our main function. And let's just do a variable here called x and y. That's right. We're not initializing them. We're just saying int xy. And then a string. So we'll do a char string, and we'll make that, I don't know, 10 characters wide. And let's go ahead and print out what those values are. So printf xy is that value, char xy, and then the string printf string is, and then inside these brackets so we know where it begins and ends, that's our string value. Now return 0. Now I've been very careful here not to do bad things, right? I've been doing bad things in this one. I'm not initializing x and y. I'm not assigning any variables to them before I try to print them out. And the same thing for my string. I'm not assigning any value to it. It's just saying go and get memory that's 10 characters wide. And that's all my program is going to do. And then it's going to just print out what those values happen to be. Now, some compilers will initialize variables to 0. Other compilers don't. The standard says it's undefined behavior. So let's go ahead and compile i16 GCC. Turn on all warnings. We're going to output this as gvars.exe.c. Vars.c. There we go. Yep. So it's giving us a warning because I turned on all warnings that FYI, you're using an uninitialized value, and that is absolutely true. Let's go ahead and, but it did actually compile. We actually have a gvars.exe. Let's go ahead and compile using OpenWatcom, and that's vars.c. Oops, I don't have the environment defined because it's rooted. Devel ow set env, and let's go ahead and run wcl and c. And that one's happy. No warnings on that one. Just happened to compile the program. So gvars, that's the one compiled with the GCC, and that one does initialize the variables to 0. I wouldn't rely on that because if we run VARs, which is compiled with OpenWatcom, we're getting a whole bunch of garbage. So be very careful that the values that you are picking up are actually initialized. Now I could do, let's try to do a malloc real quick. So let's edit that again. Fed vars.c, and we're gonna do a malloc, so we need to have include standard lib, and let's do another string value char stir. It's a pointer, right? Stir, and let's go ahead and allocate my memory. So stir is the malloc of, and then how much memory am I asking for? The size of char times, let's do 10. That's the same value, same size as my other string. Now, best practices, I should check if string actually malloc its memory. So we'll do if stir is null, then we're going to do just an error. It says put s could not malloc. Hopefully we won't get that because it's only trying to get 10, but you never know. Good behavior is, and every time we do a malloc, you should always try to verify that actually worked. And so now we can say printf stir is, and inside the brackets we're going to print string stir. Go ahead and compile that. So wcl vars.c and i16 gcc. Turn on all warnings. We're going to output that as gvars.exe and vars.c. So it's the same file again, and we're just not going to assign a value to it. Let's go ahead and run vars. And yep, again, we're getting garbage put into our values. Malloc is not zeroing it out either. And let's run gvars. And in both cases, it looks like the GCC version of malloc is zeroing out my memory. Again, let's not assume that. That could be an implementation specific thing, but you might not be using the GCC compiler all the time, right? The world is not made up of GCC. OpenWatcom definitely does not do that. So be very careful about what values you're using when you are using those variables. Now let's do another one here where we're going outside the array boundaries, right? I've been very careful to stay inside array boundaries in my example programs. So let's do array.c. And so we'll do our include standard IO, and then our main function. Oops. And then let's do an array. Array. I'm being unimaginative here. And it's 3 elements long. It's an integer array, and it's going to store the values of 1, 2, and 3. And I might do the same thing with a string. So I would do char string, and that's going to be initialized to something like hello. Right, and then we're going to iterate through this. So we're going to do an int I, sort of a counter variable. Let's go ahead and walk through that array and see what those values are. So we'll do a for loop, I equals 0. That's where the arrays always start. I is less than 3, and then I plus plus. And then we'll do a printf that says the array at that value, at that index, is, say is, and then that's the value. So the index is I, and then the value I want to pull is array I. So that is walking through our array, and I have initialized it, but it's only a three element array. So once I get to index 4, that'll break because I'm now going outside the bounds of my array. Bad programming practice. Again, this video is all about what not to do. Let's look at my string here. We'll do for I equals 0. I is less than, actually, you know what, this isn't going to break. I stayed inside the array. Let's make it 10. So we're going to be I is less than 10, because that's also longer than my string hello, and then I plus plus. And then we'll do the same thing. Printf string at that position is, we'll just put it inside these brackets so we know what it is. And then that's the position, and then that's the string position. And so all I'm doing is I'm just walking through these arrays, and I'm going well outside the bounds of the arrays, because my string, how long is my string? I've initialized it, so it's got 1, 2, 3, 4, 5, and then a null value at the end, so 6. It's actually 6 elements long. And that's how long it initialized the variable, because I didn't give it a number here. So it's going to pre-initialize that to be a 6 element array, which is a string. So by the time I get to beyond that, it's going to start pulling other things that happen to be in the memory, and I'm going to be printing out as though they're a character value. So let's go ahead and let's have to remind ourselves here. Put s. We'll just the end, right? Just to remind ourselves we hit the end of the function or of the program. And we'll go and compile that. So the Watcom compiler, array.c, and that compiled. And then i16 version of GCC, we'll turn on all warnings. We're going to output this as garray.c, and then we're going to compile the same file, array.c. We got the same program compiled 2 different ways, no errors, no warnings. So array version compiled with Open Watcom. So you can see my array was initially set to 1, 2, and 3, and those are certainly in positions 0, 1, and 2. And then after that, I'm pulling garbage. I'm pulling stuff that is just happens to be in memory at what would be the next index, 3, 4, 5, 6, all the way up to 10, right? So I'm pulling 9. So I'm pulling up just really other values that aren't part of my array. Same thing with my string, right? It's hello and then a null value. So that's why string 5 is showing up as empty. But string 6, 7, 8, 9, that's just, again, it's garbage value. It's being used by the program. It's memory that's been used somewhere, but that is stuff that does not belong in my array. So be very careful as you're doing stuff with arrays that you're not going to be going beyond the bounds. So let's do one more example here with that array. So let's actually do a malloc. So we'll do the include standard lib. And so down here, I need to have a pointer for that. So we'll do a pointer that is a, what are we going to use? Let's do, let's do an integer pointer, p array. And then down here, we're going to do a malloc example. And so p array equals malloc. How big is it going to be? So it's going to be the size of an int times how many ints do I want that to be, and let's make that I don't know. We'll do it as 6. That's how long the we'll do it as 3. It's an integer array, same as my other array that I had up on top. And so let's be good programmers and make sure that that actually works. So if p array is a null value, then I should go back to the operating system. So we're going to do put s failed to malloc. Probably should be putting that to standard error, but this is a demo program. Turn back to the operating system. So even when I'm trying to show what things not to do, I'm still trying to be a good programmer. So let's go ahead and now walk through that array. I equals 0, I is less than 10, because that's what we did up above. I plus plus. Now again, my array is only going to be 3 ints long. So again, I'm still going beyond the elements of my array. And then we'll do printf, and then p array at that position is that value. That's going to be I, and then p array. And then that's that. And now I can go ahead and free my pointer, because you can always free your pointers. And there we go. So that's what happens when I do that. Let's see if that actually still works. So we're going to compile using the i16 version of GCC. That was fine. And then compile with OpenWatcom. And that's also fine. So let's go ahead and run array. So again, I didn't initialize the array. So I'm getting garbage values in P array. But I'm also going outside the bounds of my array. So I'm getting a whole bunch of other garbage that's out on the system. It's entirely possible that that 3024 and 3024 at P array 4 and 5, possible that that's part of the L's, the double L's out of hello. I don't know what that is. It just happens to be the same value, but we're going outside the bounds of the array. We're going to uncharted territory. Never do that. And that's what happens. You're going to pull data that doesn't belong to your array, and if you are not careful about where your array starts and ends, you're going to run into those problems. Let's do the same thing with GCC. So garray. And so again, we're looks like the GCC malloc is actually zeroing out our array, which is why 0 through 5, the first 6 elements of the array, are zeros, and then beyond that, we're getting a whole bunch of garbage values. So again, it's always be careful when you are writing your C code to stay within the bounds of your array. And you know what? Before I leave this one, let me show you one other example here. So I've talked about, when you allocate memory. So we've allocated memory with malloc, and then whenever you're done with it, you should free it. What happens if you free memory twice? So let's look at what happens if we do a free of P array twice. So this time, this first time that we do free, we're actually freeing the memory. The second time that we do a free, that P array pointer is meaningless. So what are we actually freeing? We're probably going to break some stuff on that. Only free memory once. So again, this is a video about what not to do. So let's go ahead and compile this one more time. And we'll compile it with GCC. And you'll note no warnings on that one. It just works. So you might think, oh, that's a good thing. I compiled without warnings. No, actually, it can still break. And so now we'll compile it using Watcom. And there we go. No errors, no warnings. So let's go ahead and run array. Again, I'm doing a free twice. That's fine. Okay, that's good. So garray. What happens when I do with the GCC compiled version of that? Oh yeah. Okay, so we definitely broke that. When you do a double free, you're gonna break your program. So that is a pretty dramatic example of what happens when you do free twice. So be careful when you're freeing up memory. You only want to free the memory once. Now let me do one more example here, and that is when we open files, we always want to make sure that we check that the pointer to the file is valid. But what if we don't? So let's do another one here called. So we're going to do a standard program here. We'll just do an include standard IO. There's our function, main function. And let's do something that sort of is basically like the cat program or the type program. So we're going to do a file pointer to a file. And we're going to need to read characters at a time. We're going to do that kind of a version of a program. So we'll do int ch. Let's go ahead and open the file. And we're going to do p file. The pointer to the file is fopen. And what file we want to read? Well, maybe we want to read just a data file. So data.txt. And we're going to open that for reading. Now, normally I would right after that check to make sure that pointer is valid. But what if we don't? What if we just start typing our programs? We're going to say while ch equals f get c from that file pointer, which may or may not be good. And as long as that's not equal to the end of file, then we're saying, oh, well, we can keep printing stuff out. So we'll do a printf or we could do a put C, but in this case, let's do F, because I'm going to put it in these brackets so we can see what's going on. H. And then once I'm done with that, I should probably be a good programmer, right? And so close my file, F close, E file, and as long as at the end of the program, just go ahead and do a put S of says, and then I can return back the operating system. So I'm being good here, except after opening the file, I'm not checking that my pointer is valid. So what if I just blindly assume that the file I've read is okay? Well, let's find out. Go ahead and save that. Now, it's trying to read a file called data.txt, which you'll note I don't have. So let's compile it. I16GCC, run on all warnings. Going to output this as gread.exe, and we're going to compile the read.c. And no warnings on that one, so that's good. We'll go ahead and compile it with OpenWatcom, read.c. And I'm not seeing any errors or warnings on that either, so that's good. So we've got a program that's going to read a file one character at a time, but in this case, there's no file for it to read. So let's go ahead and run read.exe. Yeah, it got a whole bunch of nonsense until it eventually found a null or an EOF. So that's it just read garbage. That's interesting. Let's look at the GCC compiled version of that. So gread. Yeah, so that one looks like is saving us a little bit there, but you know, the standard says, yeah, always check the pointer that you've opened a file with to make sure that you actually opened your file. You can't blame the compiler on this one. That is totally down to the developer. So there's just 4 examples of what happens when you don't follow good programming practices in C programming. I'm going to leave it there. Before I leave, I just want to thank everyone who supports me on Patreon. You really do make this channel happen. Some of you are supporting me at a higher level, and I want to thank you here. So thank you very, very much. And that's it for this week. Visit our website at freedos.org. Join us on Facebook, follow us on Twitter, and consider supporting me on Patreon. Thank you.